Hello everybody, this is Cameron Snow with Danomics. In this video, I want to talk to you about relative permeability and how Danomics can help you on that front. But before I do that, let's start with a brief review of relative permeability. Okay, so you all have probably seen a diagram like this. This is typically something you would get back from a core report where they've gone through and they've measured the relative permeability of, in this case, oil to water at varying water saturations. So what you're seeing here is that when you are at low water saturations, you see the oil has a very high relative permeability compared to water. And as you decrease the relative permeability so as you increase water saturation, decrease hydrocarbon saturation, the relative permeability of oil will decrease and the relative permeability of water will increase. And you'll notice on the extremes here, water is immobile when you get below the irreducible water saturation, and oil is immobile when you get to the residual oil saturation, hence why we call it residual oil. So that is the basic primer here. Now, what is important about this is it tells you, hey, at some given saturation, let's say 20% water saturation, we will see a substantial amount of oil flow from our reservoir relative to water. As we get to maybe let's say 70% water saturation, we'll see significantly increased water cuts. And once we get to something around 80, 90% water saturation, the relative permeability of oil to water is essentially zero. So you will see no hydrocarbons flowing beyond that amount. And if you have a well-established relationship here, you can actually be predictive. You can say, hey, at 65% water saturation, we should see around a 50% water cut. Now, granted, we often don't have enough resolution to do that, but that is what this diagram is indeed telling us. So let's jump back over to Danomics and talk about relative permeability in Danomics. So within Danomics, we have a relative permeability module. You will find that here, relative permeability. It's about 3/4 of the way down the modules list here. And there are a couple of things that we want to give you here. We want to give you the relative permeability of oil and water, but we also want to give you the fractional flow of water, because I think this is the most illustrative part here is, will you flow oil, will you flow water, or will you flow something in between? And that is what we are trying to establish here. Now, in order to do this interpretation, obviously you'll need to go through and do calculations of all your key reservoir properties. So I would say start your workflow with, clay volume, evaluate your TOC, your porosity, your water saturations, do your reservoir flagging, and then you will get to the more advanced modules. Now, relative to this, there are two modules that are important. Obviously, the relative permeability module that we have here, but also the saturation height modeling, because that is where we have some methods that will allow us to address our irreducible water saturation. So what you'll want to do is start on your saturation height module, and if you have capillary pressure data, this is where you will bring that capillary pressure data into the system. If you don't, you'll either need to do this by analogy, or maybe consider using something like the bulk volume water method for getting irreducible saturation. Either way, you can establish a number of different models for irreducible water saturation here. And once you have done that, you can then come here to the relative permeability module. You will set your irreducible water saturation to use the method of your choosing. You can then provide a residual oil saturation, and then you can choose between two methods. There will be either a power law method or a Brooks-Corey method. So we are going to start off with the Brooks-Corey method. Using the Brooks-Corey relationship, what we'll notice is once it redoes this calculation, everything will essentially collapse down to a line here, and then we have controls for the lambda values of oil and water that will control the shape of this curve. Okay, and then the alternative method that we have is a power law method, and with the power law method, this is it's a bit noisier in here, but the power law method, is when we're looking at this, the cross plot is going to be reflecting, a much more zone by zone or sample by sample breakdown here. Now, what you would want to do to calibrate this is you would want to look at your relative permeability of oil to water or gas to water or whatever your hydrocarbon phase is there. Plots to understand the shape of those, see how that compares to what we are predicting from the logs. You would want to calibrate those in the log tracks as well. But let's talk about the interpretation and what you can get out of this. So so right now I've got my cross plot down to the Wolfcamp, and I'm gonna zoom in here to the Wolfcamp zone so we can take a look at those. And let's talk about what these results mean in here. So what this would be suggesting is suggesting that, hey, at the saturations that we have calculated here, that we would essentially expect this upper Wolfcamp, the Wolfcamp A zone, to flow water free. Now here in the Wolfcamp B zone, we can see that there are intervals here which do have probably have free water in them. And in the Wolfcamp C here, we can also see that in this interval we would expect to see more substantial water production than what we are seeing relative to this upper zone. And that's because the fractional flow of water is predicted to be higher in this area. So, you can look at right here, it's about a 50% fractional flow of water. So what that is telling us is, hey, we would expect that the reservoir would produce 50% water, 50% oil in this case. And we look at the upper part of the Wolfcamp D in here, we can actually see that, given what we've, calculated here, that we would expect a significant fractional flow of water relative to oil. And this, could suggest to you, hey, if you have trouble handling large volumes of water, maybe you want to steer away from this part of this zone. It may also tell you, hey, if you are landing zones here, let's say in this lower Wolfcamp D, and of course you're fracking these, you have potential to frack into zones that may flow substantial amounts of water depending on your frac growth there. So that is how we can use this interpretation. We can use this as a guide to help us understand how much the fractional flow of water relative to oil is in these reservoirs. And once again, it's critical that you calibrate this analysis with core data. I know, the data can be hard to acquire due to its cost, but it will help you in the long run. All right, I hope this has been informative. If you'd like to learn more, reach out to us at sales@danomics.com. Thank you.